I'd like to invite you to download and give a try my Excel file where I've copied and pasted the Airtables data from the textbook into Excel. And then I've created for myself and for others who might like to give it a try, an automated interpolation scheme to look up properties of air from those air tables. So let's get started. Hope you're interested. So I'm going to show you what the air tables are all about and invite you to download it. And then we'll take it out for a test drive to illustrate how the interpolation scheme that I offer works. And I am going to cover after that little test drive, I'm going to review what you need to already understand about air, analyzing air as an ideal gas. And when you use the air tables, you must remember that you are modeling air as having variable specific heat. And then I'll tell you a little bit about an upcoming test drive demo that I'll show you in the next video. So here's a screenshot of the familiar air tables from your textbook. Remember, how do you use them? Well, of course, the leftmost column is temperature, because properties of the ideal gas, all ideal gases, are dependent only on temperature. And as the temperature grows, wow, 200, that's a cold temperature, isn't it? As the temperature goes up and up and up, this table is so long that in the textbook, you have to flip over to the next right-hand block of columns to continue to increase the temperature. Here is the source, the fundamental data source, Keenan and Kay's gas tables. Look at this, from 1945. And so these tables continue to be used widely and accepted as properties of the ideal gas air around us. I'm going to show you, here's how you would download the Excel version that I'm offering of Airtables. You go to Jay's Toolbox, you'll click on the Toolbox menu, find then the set of files XLS docs. Then you'll open up another menu and you'll scroll down to Air Systems, Excel Air Systems. And once you click there, then you'll be able to click the download button to download this thermodynamics properties of air that I've copied and pasted from Moran's air tables. Okay, a quick screenshot before we go live. Of course, what I've done is the data I've put into one long set of rows, and let's see, 1, 2, 3, 4, 5, and 6 columns. And here's the screenshot of what those column headings look like. You'll also see in my file that I've only got 4 tabs in this file. 2 of the tabs are associated with SI units. The other 2 tabs are associated with English units. So you and I don't have to go back and do units conversions between units. And then this lookup, the lookup scheme, notice how it's arranged is remember in my work, a yellow cell is a manually entered number. So this is something that the user, either myself or you or any user, would enter a numerical number, and the other values are interpolated from the steam table or from the air tables worksheet. And so it's pretty straightforward if you study it, but I'm offering it to you so you can use it right out of the box if you wish. And so let's see, we're almost ready for go live. An important reminder, and that is what I just mentioned. Whenever you see a yellow cell in my work, that means that the user, you or me, enters a number in that cell. Cells that are not colored, clear cells, are Excel formulas. And in this case, they're formulas in which we look up, or I look up, the best match rows that straddle the input numbers, whether it's temperature or enthalpy or internal energy. It looks up the best match rows that straddle the input number, and then it goes out and linearly interpolates for the other values within that table. And the beauty of the reason this works is the fact that for ideal gases, all the properties depend only on temperature and not on pressure. Okay, so this is my cue to go live. So let's see if I can remember how to do that. I'm going to escape out of PowerPoint, but I'm going to stay in share screen. Here we are in Excel, but no file is open. Now, I have already downloaded the file. I possess it on my PC, and I'm going to click on it in my recently opened. And there it is. So here is Moran. That's the name, that's the author of the textbook. Air props lookup. And let's see what I've got. 4 tabs at the bottom of the sheet. The first 2 tabs are for in SI units. Second 2 tabs, English units. Let's scroll down and look at, this is just, this air props SI is purely data. There's no computations on this worksheet. So let's just scroll down. And you can see that it's just one long set of rows of all the values going from very cold, 200 degrees K, very cold, up to very hot, 2250 degrees K. And of course, here's all the properties associated with those temperatures. All right, now let's go and look, let's click on the next tab, look up SI. This is where, because I was solving so many problems for air using ideal gas with variable specific heat, in other words, using the air tables, what I did was I created a set of interpolating formulas. And so let's look at the most straightforward one first. So notice here the repetition. Here's our data. This is data we're praying to be able to get out of our air tables. Well, in this case, I'm going to, let's get one that doesn't matter. Let's say it's 292, so a very strange number. Okay, so I manually enter that number, and this interpolation scheme goes out and it finds the best row in Excel that the 2 rows that straddle this number 292. Once you have those 2 rows, it's very easy to interpolate for the rest of the values. Say, okay, that's pretty cool. Okay, but think about your homework problem solutions where you have to back calculate. Let's say you might know PR. You might have a problem in which you have solved for the variable PR, and it turns out to be 1.200. And you look for PR in the table. I don't see a 1.200. I'm going to have to interpolate because I'm looking for the temperature and the enthalpy for PR equals 1.2. Well, I've created, again, very similar interpolation scheme where I go to the PR column. I look for the 2 best match rows, the 2 rows that straddle the number 1.2. Once you have those 2 rows identified, it is a simple interpolation to back calculate all the other properties. I hope you get the, and so, well, let's see, that was an example where I entered PR. And so the same thing applies if you have enthalpy, if you have internal energy, if you have S0, that would be the zero pressure entropy, or if you have V sub R. So I hope you get the idea. Okay, let's flip over to the 3rd tab. You see they're very similar, but notice here that we've got different units. We're over in English units now, so the raw data is degrees R, and H and U units are BTUs per pound mass, just like in the textbook. Okay, and then the lookup's English, the same kind of idea here. And so remember, 530 degrees R, there may be a perfect match for that. Okay, and so I could put some strange number 531, and you get the idea that the interpolation, the linear interpolation is done for you, or I've created that for you. You're welcome to dissect it. Also, if you're interested in, well, how do you do that? I'm kind of interested, Jay, in how you did that. I've got another application that is similar. How did you do that? I will be happy to work with any of you offline, one-on-one, to explain to you. Notice here, look at this cell, interp at right. And so I can explain to you in detail how I get all of these are formulas, okay? I'm just clicking in Excel and sort of getting lost in my own work. But these are just basically Excel formulas that do the linear interpolation for you. It's not that hard once you understand what you're doing. Okay, that is, okay, let's see. So do you see how you could use this tool right out of the box? So you open this up, you say, look, I'm working on my homework problems, and I've got a value for P sub R. It's 1.36. So I'll type that in, and I need to know temperature and an enthalpy. And so instead of you're going in and doing the interpolation work, you can quickly get these results. Now, I do want to remind you that you need to get good at this manual interpolation to prepare yourself for taking quizzes and tests, because this won't be available to you when you're taking a quiz or test, will it? Highly unlikely. So you need to satisfy yourself, give yourself enough practice on manual interpolation within the Airtables so you can perform well on the quizzes and tests, not just speed up the speed with which you do your homework problems. So that's an important reminder that just popped into my head. Now, and then notice here that these interpolations are so simple that in the demo that I'm going to do in the next video, I'm going to show you how to simply copy and paste a block of these cells, get those into your clipboard, paste them over into a problem that you're solving in Excel. And as long as you have the raw data table, Moran property SI or English, then you're good to go, and you can incorporate this automated lookup into your own Excel problem solving. Okay, and so let's see, I want to continue to share. I want to go back to PowerPoint and pick back up. So we just looked at that. Reminder that tabs are interlinked. And so these interpolation cells, interpolation scheme is linked to the raw data table. And so that's why you have to start with this file. You can't just copy these formulas over into a different file and expect them to work, because they must have that other raw data worksheet or tab that I call it in order to do the interpolation, to find the raw data. A quick reminder on things you must already understand in order to speed up your homework solution speed using Airtables, these Airtables for properties. So think back about what you have to do when you read any thermo problem. You identify the substance, and is it a phase change substance like steam or refrigerant or ammonia? This doesn't apply. Then you think, is my substance an ideal gas? Oh yeah, ideal gas. Then you say, is it air? Yeah, okay, we've got air. CO2, the Airtables aren't going to apply. Then you've got air, and how will I model the specific heat? If the answer is, I've got a pretty wide temperature range, I want to model the specific heat as a variable, not a constant value, that's when you use the Airtables properties. Okay, so as a reminder, key fundamentals about ideal gases: R equals R bar over molecular weight. Molecular weight of air, 28.97. For any ideal gas, P times little v is equal to RT. Has nothing to do with those Airtables at all. Okay. For the Airtables, remember that internal energy, enthalpy, and other properties are dependent only on temperature. U is a function of T only. H is a function of T only. Remember that for any ideal gas, C sub P minus C sub V always equals the constant R, whether C sub P is variable or constant. And then remember that delta U is the integral of CV dt. Delta H is the integral of CP dt for all ideal gases. And so when CV and CP are variable and you have air, that's what enables you to go to the Airtables. Okay, I think I just covered that. How to go from basic definition all the way to applying to all ideal gases with variable specific heat or constant specific heat. Just covered that. CP minus CV equals R. And let's see, 2 key points. I think you've got it. If you have air or any ideal gas with constant specific heat, the integrals are easy, and you will not use the air tables when you're instructed or you've decided to model the air as constant specific heat. Variable specific heat and air, that's what enables you to go table A22. And this is a repeat of your decision tree for ideal gases. And I'm not going to drag you. This is just as a courtesy to ultimately to remind you, this is what we're talking about right here. Do I have an ideal gas? Yes. Can I treat it specific heat as constant or variable? I'm going to make it variable. Do I have air? Yes. Air and variable specific heat. Use table A22. Another reminder that you must understand in using table A22, the air tables, and that is that these 2 columns that are boxed out in the text, these 2 properties, P sub R and V sub R, are only used when you have an isentropic, reversible adiabatic process. Very critical. Many students think that this is pressure. This is not pressure. It's P sub R, the relative pressure and relative specific volume, with strange units all unto themselves. PR and VR used only for isentropic process use. So let me give you a little teaser for the upcoming demo of, I'm going to try to show you how to start from a blank slate and solve an air problem using the air tables in Excel. So here's the problem statement. I need to use an air compressor for a steady flow of 11.3 cubic meters per minute, volumetric flow rate of air, at 100 kPa and 25 degrees C going in and being compressed to 793 kPa. So some strange pressure being compressed to. And the question is, what is the minimum power needed to run the compressor? What's the minimum power needed to run the compressor? Think about that. How would you attack that problem? Now, if you have not yet been through chapter 6, you will not know how to solve this problem. If you've been through chapter 6 and got an understanding of continuity equation, first law, and second law relative to reversible and adiabatic processes, then you can solve this problem. And so think ahead. And if you've gotten through chapter 6, you will see nearly immediately how to solve the problem, and I'm going to try to show you how to solve that in Excel. So what are the takeaways? I've showed you and offered you how to download and use this Excel Airtables tool as a standalone tool to help speed your homework solutions when you have air, variable specific heat. So you must understand when to use the Airtables, and also recognize the importance of units. Very important. Do you have SI units or you have English units? And you must keep those straight in all of your solutions. Okay, so I hope that helps. I hope you're interested in taking the Airtables Excel file out for a test drive. You'll see that once you've mastered the manual interpolation of those Airtables to prepare yourself for quizzes and tests, then give these Excel Airtables a try to speed your problem solving of your homework.